Let's review some important things that we've learned so far this year. The nucleus has the protons and neutrons, but something we haven't talked about before is why those protons and neutrons stick together. Because it makes sense that the protons are all positively charged, so don't we know that like charges repel or move apart? So there is a force that's keeping those protons and neutrons together instead of making those protons repel one another. That force is called the strong nuclear force. And if it is not strong enough in specific cases, we say that the nucleus is unstable. Well, the way that happens is if there is a large difference between your protons and neutrons. So we know that protons and neutrons might differ by like 1 or 2 neutrons typically. But if that difference increases by a lot, then that's what causes the strong nuclear force to not be strong enough and making our nucleus unstable. Other things to review are that the atomic number tells you how many protons are in an atom, and that also determines the identity of the element, since all of our elements have a different atomic number. The mass number is how many protons there are in that atom, plus how many neutrons there are. And isotopes are elements that have the same number of protons, so they're the same element, but they have different numbers of neutrons, which also causes them to have different mass numbers. So this unit we're going to be talking about radioactive isotopes, and they are also called just radioisotopes as well. So they are going to be isotopes, but they are atoms that have that unstable nucleus that we were talking about previously. In order to become stable then, it goes through a process which we call nuclear decay. So it's going to release what we call radiation. That radiation will take place in 3 different ways: alpha decay, beta decay, and gamma decay. Alpha decay is when that atom releases 2 protons and 2 neutrons. So here's an example. Uranium has an atomic number of 92 and a mass number of 234. If it releases an alpha particle, which is 2 protons plus 2 neutrons, which would give us a mass number of 4, which is really just a helium atom. If we release that alpha particle, my atomic number has decreased by 2 to give us 90. And the element that goes with the atomic number 90 is thorium. So uranium is becoming thorium. It's changing elements. That's big for us because we haven't had that happen before. In a chemical reaction, which we did last chapter, that cannot occur. But since this is a nuclear reaction, then we can change elements. And in this case, it's from uranium to thorium. When we have a change in elements like that, we call that a transmutation. Beta decay is when we release an electron. This happens when one of the neutrons basically transitions into becoming a proton and an electron, and that electron then is released. So in this case, I have iodine with an atomic number of 53. If one of the neutrons becomes a proton and an electron, and that electron leaves, that means I've added a proton. So my atomic number is now 54, and that element is xenon. Gamma decay is when you just release energy from the nucleus, and that's usually going to happen along with beta decay and alpha decay. So in alpha decay and beta decay, we're releasing particles. Gamma decay, we're just releasing energy. We can use our radioisotopes in many ways. One way is a tracer, which is what you use in medicine. So for example, you can use the radioisotope iron 59 to trace the circulation of blood so that you can see how the blood is circulating more easily. You can also use these radioisotopes to find leaks, like radon leaks, for example, in a home, or to find weak spots in a foundation. So radioactivity in general is when an unstable nucleus ends up emitting radiation. So as we said before, alpha particles, beta particles, and gamma rays. So those charged particles are the alpha particles and beta particles, and the energy are the gamma rays. That radiation, as we said before, has a few uses. One other use is that it can be used to kill cells. So we obviously don't want it to kill good cells. We want that radiation to kill bad cells, such as cancer cells. Radioactivity was discovered by Becquerel, and he discovered them when he was doing experiments with uranium salts. Two other important scientists for us were Marie and Pierre Curie. They were a husband and wife team, and they discovered the radioactive elements radium and polonium. Polonium was named after Poland because Marie Curie was from Poland. We can detect radioactivity by using an instrument called a Geiger counter, or by using a film badge, which is just, it's literally just a little badge that someone who works around radiation puts in his or her pocket, and then it helps to detect the radiation so that he or she isn't being exposed to too much radiation. So as we saw on our previous slides, our elements can become new elements, or they can transmutate. The rate at which that transmutation or that decay occurs is always constant. It doesn't depend on temperature, for example, or the amount of stirring that we talked about in our last chapter. So we can use this information to our advantage. However long it takes for one half of the radioisotope to decay or to transmutate into the new element, however long it takes for half of that to happen, or for half of it to decay, is called its half-life. So here's an example that shows what I mean by that. So the parent material is the material that you start with. So on a previous slide, for example, we started with uranium. So if I start with 100% uranium, after one half-life, half of it will still be uranium, but the other half will have changed into the new element, or the daughter material. So in the case of the previous example, this would be my uranium, the old stuff, and the new stuff would be the thorium. After another half-life, things get cut in two again. So my uranium is now only at 25%, and my thorium is up to 75%. After another half-life, my uranium splits in half again to 12.5%, and my thorium increases to 87.5%. So my parent material is getting less and less and less, and my daughter material, the new material, is getting larger and larger and larger. We can use that information about half-lives to determine how old something is, and that's called radioactive dating. So here's an example. The half-life of carbon-14 is 5,730 years. Carbon-14 transmutates to become nitrogen-14. If you have a 100-gram sample of, something, some sort of sample, and 25 grams is carbon-14, and 75 grams is nitrogen-14, how old is the sample? Well, first we have to figure out how many half-lives it's been through. So when it started, it was all carbon-14, and there's only 25 left, that means that I cut that 100 grams in half to 50, and then I cut it in half again to 25. So it's been through two half-lives. Each one of those half-lives is 5,730 years. So I do 2 times 5,730 to find out that my sample is 11,460 years old. We can do this sort of math with lots of different materials. Specifically, we can do this for fossils using carbon-14 and its half-life, and we call that carbon dating. Two specific nuclear reactions are fission and fusion. Fission is when you take a nucleus and you split it. The energy that's produced by that process can be used to boil water and run steam generators that produce electricity for us. This is what it looks like. If I add a neutron into a uranium-235 nucleus, it makes that nucleus become unstable. So it ends up breaking apart in order to become more stable. When it does that, that nucleus splits into two pieces and it releases a lot of energy. Also, some of the neutrons that were in that nucleus have come out, and they're going to go and they're going to hit other uranium-235 nuclei that are hanging around. When they hit those, it's going to be the same thing that happened here. Energy will be released, that nucleus will split into fragments, and neutrons may be released, which will then go on to hit other uranium-235 nuclei. This idea of one nucleus causing several things to happen afterward is what we call a chain reaction. Fusion is the opposite of fission. Instead of splitting a nucleus, we're going to take two nuclei and we're going to combine them. This is what happens in the sun. And as we know, the sun is producing a lot of energy. So a lot of energy is also released by fusion. This is what happens in our sun, but also in all of our stars. That's what makes them release so much energy in the form of light and heat. This requires extremely high temperatures, however. So we currently are unable to use fusion to produce electricity like we are with fission because of the limitations that we have here. So both fission and fusion are going to end up producing a lot of energy from only a small amount of mass. So again, from just this one nucleus, I'm producing lots and lots of energy.